Okay. I hope you guys can see the slide okay?
Yes.
Okay, great. Yeah, so my name is Michael Ko. I'm in charge of new business development at Vitex. Today we'll briefly cover overview of 800 gig optics, specifically related to data center interconnect. So we'll cover, the basic drivers behind the transition to 800 gig, and there are a few key technologies and terms, form factors in 800 gig. So we'll just share a brief overview of 800 gig optics and key technologies. And then we'll also discuss a little bit about our perspective on what we are seeing in the optics marketplace. Then we'll close the presentation with what we offer in this 800 gig space, and we'll leave some room for Q&A in the end of the presentation. Okay, and feel free to stop me with any questions during the presentation as well. I like to be interactive. And of course, all the drivers behind the 800 gig adoption is really the AI and AGI investment. It's no secret that there has been a lot of investment into computing power, bandwidth, and networks. And just one figure that that come to our mind is that NVIDIA just reported huge increase in their revenues, in profits, and all those GPUs, of course, need to get connected together, networked together, in processed information, and to develop the AI models. And the current status is that, as most of you know well, 800 gig is the latest, the fastest optics that's available commercially. 1.6T is also coming up pretty fast. So there are some products already being released. But right now, starting last year, 800 gig really has been adopted very fast by various AI data center customers. So just to share the highlights, we picked this out of a recent New York Times article, and you can see that in the last few months, the monthly investment into data construction has been over $3 billion. So the growth and the investment into space has been pretty amazing, starting in late 2023. So technically speaking, for 800 gig, of course, that you double the bandwidth from previous 400 gig optics. So if you look at from the switching perspective, a typical switch will have 32 ports. So by moving from 400 gig to 800 gig, you could increase the whole bandwidth density, if you will, all the way up to over 25 terabits per second, right? Or 25 terabits per reg unit. And because of the migration that we had in the past in the optical space from 100 gig, even some 200 gig, 400 gig to 800 gig, it's easy to break it out or aggregate 400 gig to 800 gig or vice versa. So there are some good products already available to enable that. So that's also another benefit. And of course, that's the reason that NVIDIA adopted 800 gig ports in most of the systems, including quantum and spectrum switches. So then 800 gig, just like many high-speed transceivers, there are two types. First, we'll talk about the transceivers. Most of the transceivers in 800 gig space, they cover 50 meters, 100 meters, 2 kilometers. There are some 800 gig optics that can cover even 10 kilometers or beyond. But for most of within data center applications, I'll say 2 kilometers or less will be predominant, and that's what's being used. Outside of the transceivers, there are cable products, and we'll talk about different type of cables that's available. But by its nature, it's relatively short distance. So I would say, depending on the application, 10 meters or less. Although some active optical cables can go longer distance, but there are, just depending on your connection application, and then also the frequency of the connections, you have a different choices in terms of transceivers and cables. When you open up the optical transceiver, 800 gig optical transceiver, these will be key building blocks you'll see. So when the optical module, which is represented in a kind of a gray box here, the top portion is a transmitter, and you have 8 lanes of 100 gig data rates coming in. Of course, go through the CDR digital signal processor to handle such high-speed data rate. And you have drivers to amplify the signals and go through the lasers, get converted into optical signal, and get to send it to the other side of the network. The bottom side is the receiver side. And essentially, you have the similar optics and electronics in the reverse order. And with that picture in mind, I can go a little bit more detailed into some of the details of key components. So as you talked about that, from the switch, you start with 8 lanes of 100 gig electrical lanes. Pretty much all 800 gig optics utilize 8 lanes and 100 gig data rate per lane. And because it's such a high data rate, we employ what's called the PAM4 modulation, and that there's a chipset for digital signal processor to handle the error corrections and signal integrity. And those signals go through the drivers to amplify the signal, and then lasers get used to essentially to encode those signals onto optical signal. And typically in 800 gig optics, you'll find few different type of lasers. For our application, we typically use either VCSEL or DML. So the VCSEL typically gets used for short reach applications. Again, short reach meaning 100 meters or less, typically. And for directly modulated lasers, we typically employ that beyond 100 meters, or maybe 2 kilometers, even 10 kilometers. The EML, that's really for really long distance applications. So for our purpose, you are not going to see that many EMLs in our optics. Again, for 10 kilometers or 2 kilometers or less, you most likely you'll see VCSEL or DML lasers inside the optical transceivers. And those obviously gets transferred through 8 by 100 gig optical lanes and go through the optical fibers. And just going back to the slide again, on the bottom side, when the optical signal comes in from the right side, we have a photodetectors, we have a transimpedance amplifiers to condition and amplify the signal, and again go through the chipset, right? And before it goes to the 800 gig switches. So those are the key components. And many of these modules, I should say, many of these components get used, even the low speed optical transceivers, but the DSPs is obviously something unique in 400 gig and above. And so we'll talk about the DSPs a little bit more in later presentation. Probably one of the important information is that there are two different form factors that's widely available at the moment. One is OSFP. OSFP standing for Octal Small Form Factor Pluggable. So Octal obviously means 8. So that's we talked about 8 by 100. That's where the 8 comes from. So OSFP that form factor is designed to handle 8 lanes. Physically, this form factor OSFP is larger than QSFP-DD. So that's in a way that's I guess disadvantage. But because it's larger, you do have a better heat dissipation, especially when you integrate the heat sink. Industry sometimes called it IHS, and that's type of a product you see on the right side in the picture. And as I mentioned, OSFP really got developed starting with the 400 gig, and now it's being really widely used in 800 gig. And for 1.6T, pretty much we think that OSFP will be dominant form factor. The typical power for this form factor is around 16 or 18 watts for most of modules. The one interesting, I guess, the difference or different version that's available is there is a version without the heatsink. It's called RHS. And that one, so physically they are different. It's RHS is a smaller profile with a lower height. So maybe you can see it better in the next slide. So one on the left is, I would say, default or standard OSFP with a built-in heatsink. You can see that the height is about 13 millimeter. One on the right is without the heatsink, or again, industry call it RHS. So you have to rely on the heatsink within the switch, essentially, right? So either air cooling or liquid cooling within the switches because you don't have a built-in heatsink. But it's a lower profile, 9.5 millimeter. So it gives you more density and it's a smaller size. So yeah, we just have, and because of a different size, you cannot put one into another port or the other vice versa. Yeah. So, we just have to be careful when you say OSFP. Just need to know whether it includes the heatsink or it doesn't include heatsink because it doesn't make a difference, especially in height of the module. So the other popular form factor is a QSFP-DD. So it stands for quad SFP double density. Now quad stands for 4 lanes. So this one particular, when you have a 4 lanes, so QSFP has been around for a long time, even from 40 gigabit per second data rate. So it's been around for quite a bit of long time. But when you have a double density, so you have a 4 lanes, but you have a kind of a double connectors. So that enables 8 lanes. So that's how it gets applied to 800 gig transmission. Physically, they are smaller than OSFP. The power consumption, I would say comparable with OSFP, about 16 to 18 watts. Big advantage is they are mostly backward compatible with previous QSFP generation, like the QSFP 2800 gig or even 40 gig or even some of the 200 gig. So there are a few different form factors based on QSFP. So that's probably one advantage it has over OSFP. So when you look at the 800 gig optics, you'll see a few different connectors that's available. And some customers ask us about differences and what they look like. So I thought it would be useful to share what are some popular connectors you'll find in 800 gig optics. Dual CS is a relatively new connector, and it really got developed for high density, high speed connection. So I know all these pictures got blown up, but that's what it looks like, what's called dual CS. I'm sure a lot of you are familiar with duplex LC. This one, it has two of a duplex LC, again, to enable the more connections. And then there's even such a thing as a dual mini LC. Again, these are all different orientations, and this is what they look like. More commonly, you'll find what's called MPO connectors on 800 gig optics. So you'll see some of the 800 gig optics with MPO 16. And as most of you know, it has 16 fibers already built in, 8 lanes for transmitter, 8 lanes for receiver. As we go into 800 gig optics, the dual MPO12 has been more popular. And this is because, as you can see kind of in the photo in their circle, there are a lot of 800 gig optics that's coming out essentially 2x400. So it's almost like you have two 400 gig transceivers built into 800 gig package. So you can imagine that when you deal with 400 gig optics, with each MPO12 can get connected to 400 gig optics on the other side. So it makes it very convenient, the connection between 400 gig optics and 800 gig optics. And so you'll find the dual MPO12 in those applications. So this gives you some ideas of various connections you can make. There are a lot of different examples or configurations you can make, but just as a representative examples, the first one, for example, you have what's called the 2FR4. So that's essentially 2x400 FR4 built in. into FR4 typically is about 2 kilometer reach. And that particular transceiver on the left will have a dual MPO 12. So, you can connect the, I'm sorry, not dual MPO, this is LC connectors. And then, so that gets connected into 400 gig FR4 on the other side. One in the middle is for the short reach, about 50 meters. And in this case, you have MPO connectors on both sides. So this will be a case of a dual MPO 12 type of a connection. So you connect it into your 400 gig VSR4 on the other side. And then you can even make it break it out. So we kind of show you an example in this case. You can break it out all the way up to 8 by 100 gig optics. And there are some examples you can do 4 by 200. Or of course, you can do 2 by 400, and you can make some combination. So these are some practical connection examples or configurations you can make depending on your network requirements. As I mentioned previously, DSP is probably the critical component in heterogeneous optics. So I think it'll be worthwhile for us to spend a couple minutes on DSP. Depending on the DSP deployment or how many DSPs you use, the standard 800 gig optics will use essentially two DSPs. One DSP on the transmitter side, the other one on the receiver side. So it's a fully retimed. Your signal is a very high quality. So that's all great. But the downside is that DSP does consume a lot of power. So it has to use a lot of power. And of course, the DSP can take up, I would say, even up to 25% of the overall optical module cost-wise. So it does increase the cost. But you do get great performance, of course, by having these brains essentially in the transceivers. But because of a lot of switches now have a very good, essentially DSPs on their side or very good SerDes on their side, the people realize that maybe you can remove some of the DSPs or remove DSPs altogether and still make the link work. So one example is what's called linear receiver optics, and that one removes the DSP on the receiver side. So you have a DSP on the transmitter side only. Because that you use only one DSP compared to the standard optics, you use lower power and it's less expensive. And you can kind of say that you can have a pretty decent system interoperability because just by concentrating your retiming within a single DSP, especially if you use the optical modules from same vendors, you can actually have a very decent link. And then you can have a good savings in power consumption as well as cost. By going one step further from linear receiver optics, you can remove the DSPs altogether. So that would be the picture on all the way to the right. So there are no DSPs. So that means you have a lowest power, probably the lowest cost optical module. But obviously there will be some signal integrity challenges. Again, depending on the network, if your switches are really well established, the great SerDes, and your link is relatively short, it's well known, then even the LPO could work. So really driven by the system considerations. And I just want to mention this because there are different optics available with the different trade-offs. So in our view, where LRO, LPO makes sense is, again, because the DSP, I mentioned about the cost, it's up to about 25% of the overall optics module cost. But power-wise, it actually uses a lot more, up to 70%. So if you have enough signal integrity from high-end switches and built-in DSPs or SerDes electronics, especially a lot of NVIDIA products, LRO, LPO actually we think makes sense, especially your application calls for lower power consumption and improve the latency. So by not having DSP does take a lot of processing power, processing time. So in certain applications, you could improve the latency quite a bit by removing the DSP, obviously, right? So that can be critical for certain applications. And we recommend that when you use either linear receiver optics or linear pluggable optics, it probably makes sense to use the modules from the same supplier so that you guarantee the compatibility and the performance. Um, and also that whether it's a training versus the inference, depending on the application and model, latency, network integrity, they have a different, I guess, the emphasis or different priorities. So that could also drive your decision with what type of optics that you want to deploy in your systems. So we talked about the transceivers. The cables are simpler in the sense. There are, I would say, three large categories of cables. One is the DAC cable. It's a simple copper cable. Typically 800 gig speed. We say about 3 meters, even 2 meters. That's about the limit. And in order to increase the reach a little bit, some people put some chipsets inside to amplify the signal. And those AECs or active electrical cables can go up to about 7 meters. I can just show you some of the graphics. So the DAC one in the middle is a simple copper cable, straightforward, probably the most cost effective. But even at 2 meters and 3 meters short distance, at 800 gig speed, these cables are bulky and heavy. So some customers really, when you have so many of these cables going around, it can be physically challenging to handle these. I mean, AEC is still copper-based, but you can go a little longer distance, probably up to 5 or 7 meters. But the AOC, which is one on the top, active optical cable, essentially has a simple transceivers on both ends. So you can handle the optical to electrical, electrical to optical conversion, and all those nicer things. So you can really expand your reach. I would say even up to 50 meters. You can go even longer, but probably up to 50 meters is a safe bet. While they are a little bit more expensive, because you use fiber optics, it's very light, easy to handle. So when you have hundreds or even thousands of these connections going on within the rack or between the racks, it could actually make a difference. So again, these are different products are available, and depending on your system considerations and what's really important. So these are some of the deployment examples, and some pictures actually, this happens to be just breakout cable in a way. So you have 800 gig transceiver or 800 gig and on they can connect it to InfiniBand switch, and then you can break it out to 4x200 in this case, and they get connected to your various NIC cards. The other example might be that you have, again, some twin port meaning 2x400, and you can have that on your either quantum or spectrum switches. On your right side, your network interface side, or network NIC card side, you can have a 400 gig devices. Again, as configuration examples we discussed earlier, you can make various different connections between your 400 gig NIC cards and to 800 gig switches. And this is another example of, you have a 2x400, which is 800 gig short reach device on the left side. That's connected to your quantum switch. On the right side, you have a HCA card, which has a 400 gig. And this is not even breakout because you already have essentially a 400 gig transceiver built in, two of a 400 gig transceivers built in into 800 gig. And you just make a straightforward connection between 800 gig between two of a 400 gig to the right side, right? So commercially, what's happening in the data center market, and this is just our perspective. the vast majority of all this demand really comes from the large hyperscalers and tier one companies, and these companies are very well known. In optics space, there are very good capable tier one suppliers such as Coherent, Inolite, or Lumentum. These companies are very good. And I used to work at Lumentum, so these companies make great products. But because of this surge in demand, their capacity is pretty much all tied up. So that's one kind of a challenge. And the other challenge is that many of these tier one AI data center customers, in often cases, they have their own custom requirements, custom optics for the specific application. So the tier one optics suppliers really have to serve these custom optics for specific application. Again, the demand, we are talking about millions and millions of units. So that's, in a sense, it's a great business, but they have to serve this large demand from tier one AI data center customers. So we see that some of the rest of our customers out there maybe could be startups, some of the new the neo cloud customers. I think that they are also looking for some viable optics partner that can deliver on time, that could offer on-time delivery and the local technical support. And so that's the kind of a space that the Vitex has been playing in. So essentially that we become a optics partner of choice for many emerging leaders by offering good technical support and quality 800 gig or even 1.6 optics. And since we are based in New Jersey, I think that we've been working very closely with some of the local customers. So that's our value proposition to many emerging customers. And here's a snapshot of our 800 gig and 1.6T optics portfolio for AI data center applications. So we're actually sampling some of the 1.6T already also, which is a OSFP DR8 and 2x FR4. That's on the table on the left side. And of course, the bulk of our offerings is for 800 gig and SR8 or the DR8. So these are different reaches as we talked about, 50 meters, 100 meters, 500 meters, up to 2 kilometers. And we also discussed some of the different flavors of cables, AOCs, AECs, and the DAC cables. So we have a few different flavors on 800 gig and some of the 400 gig to match the customer applications and their networking needs. Now, I just want to show you some slides of our manufacturing the facilities and what we are doing. So these are some of the optical assembly that goes into 800 gig optics and some testing. These are some of the inspections that we need to do at high-speed optics. Some of our factory, the equipment and the facilities. And of course, the testing is actually very important. So these are some of the testing that for transceivers as well as the cables. So in conclusion, we just gave you a very short overview of a few different 800 gig optics, but I think that it's really depending on system needs. And as we mentioned that some form factors is better for backward compatibility, or some form factor like OSFP might be even better for forward compatibility. And there's a lot of important considerations besides the bandwidth, power, cost, availability, interoperability, and lead time. And so, of course, those are all important considerations as you move forward in 800 gig and even 1.6T and beyond deployment. So that's the end of the presentation, and I'll be happy to take any questions that you may have.